Now we're going to define a type of cross-validation called k-fold cross-validation. So we saw in the previous video when we did holdout cross-validation that introducing our validation set gave us a chance to assess our model performance and then iterate. And it gave us a view into how the model is going to perform on your one particular set of unseen data, in this case, the validation set. But it's possible by random chance that our validation points are not representative of unseen data that the model may encounter. And so one way that we can look at this is to try different training validation splits. These are mean squared errors from our vehicle model with different training and validation splits. And we can see that in one of those I get a very low mean squared error of 14, but that's not as typical for the other two, right? And so this idea of wanting to capture the fact that, we just had one set for our validation error and perhaps it's not as representative, we're going to address that in a process introduced now called k-fold cross-validation. So I want to assess my model performance on several different validation sets. So in our original split, right, we were setting aside some percent of training data. And I said typical standard practice is between 75%, 90% of your data for training. And again, it's based on the size of your data set, the complexity of your model, how much you want to set aside. We were doing, for example, 20% for validation and 80% for training. But I could have selected any 20% portion of the training data for validation. So I want you to imagine now if I take my original data set and split it up into 5 different groups of 20%. In total, there's 5 non-overlapping chunks of data points that I could set aside for validation. So this is what I'm going to use. A common term for one of these chunks is a fold. And if you are using 5 folds, then each of those folds will consist of 20% of the data points. Another way to think of this is we can think of ourselves as having 5 hidden validation sets in our training set. So in cross-validation, we're going to perform validation splits for each of these. We're basically going to do 5 different rounds of fitting the model to training and then testing it on our validation set and seeing what mean squared error we get from our validation set. Okay, so for a data set with k folds, pick one of those to be the validation fold, train the model on the data from the rest, right? So not from that fold. Compute the model's error on the validation fold, record it, repeat this. So if I'm doing 10-fold cross-validation, I would do this a total of 10 times. And then I take the average error across all of those 10 validation folds. And that's what's called our cross-validation error. So visually, if I'm doing this with 5-fold, you can see I train the model on the other folds, compute the mean squared error on V1, do the same process for each of these, and then my cross-validation error is the average of the mean validation errors on each of these 5. This will help us account for the fact that, sometimes we might just be unlucky in the way that we split up our data. So let's actually go look at this now in our notebook, and let's try looking at the vehicle's data set and using this process of k-fold cross-validation to help us pick the best degree polynomial to use for our model. As we do that, I want to point out, before we do that, here's our model selection workflow. We started with the full data set. I split it up into my training and my test set. And then I take my training set and split that up into k folds, right? So if I want to do fivefold, I'd split this up into 5 separate validation sets and train my model 5 different times, and then calculate my 5 different validation, mean squared errors, and average them. Before we do this, I want to add some terminology here as to what we're actually selecting for. So we often use cross-validation for what's called hyperparameter selection. In our example, our hyperparameter is our degree of k that's controlling the order of our polynomial. And so I am going to do this process of cross-validation for different degrees of the polynomial and then pick the degree that gives me the lowest cross-validation mean squared error. And again, in this process, I'm using the training set, therefore, to select my parameters like my theta, but then I'm using the validation set to really select what power or what degree of the polynomial I want to use. Today, we're just using k-fold cross-validation to select a degree. What we're going to see in our next lesson is there's another use for this in selecting what's called a regularization penalty that will also be helpful in making sure we don't overfit our models. Okay, so let's go to the notebook, practice this, and then we'll come back to the slides. So I'm still in the cross-validation notebook, and I'm just popping back to the plot that we created in our last video using the holdout method. This was our validation mean squared error. We used it to choose model complexity of degree 8. But I wanted to point out, right, that there's very minimal difference between 2 all the way up to 11. So choosing 8 is probably a little bit of overkill, especially when we look at the variation. I mean, like 5 here is just about as close as 8 in terms of the mean squared error. And so this is really where using k-fold cross-validation is going to help us realize if maybe we were being overly sensitive to particular things in this validation set. The other kind of red flag that I saw when we created this original model was then when we went and did our test mean squared error was way bigger. It was 20, right? It's much bigger than our validation, which is common, right? The test is usually going to be bigger than your validation, but not always that bigger, which makes me think there might have been something more unusual about this validation set. It's not as representative to have such small values. So this is going to come out in the cross-validation or the k-fold cross-validation process. So let me show you what's happening here. This is the code I used to create the output I had in the slides, which was basically, let's just do different train validation splits. Like I'm randomly just splitting them up and then calculate what is my validation error. And so you can see, right, it's varying quite a bit, 17, 14, 16, 26. So that number 11 that we got was probably an outlier, pretty low, not as usual, right? And the more I do this, you can kind of see it popping around. So this is what k-fold is going to help us take into account. It's basically going to do the same idea, and then we're going to average these mean squared errors. So first, I'm just going to do k-fold cross-validation for our model using polynomial of degree 8. Okay, then we'll change the degree, but let's do this in 2 steps. So first, there's a built-in function called k-fold that's in sklearn that will help split up your indices into however many folds you choose. And then you can loop over those indices by calling this, right? So this will give you the training and your testing indices, and then you can pop those into your actual data frames. So what's happening in this process? Here I am splitting the data into 5 non-overlapping chunks, and then I'm pulling out the indices for each of those chunks one by one. So like for the first chunk, let's get the training and the validation indices, and then I'm defining my X train and my X validation using those indices. Then I'm going to train my model on just the train and then calculate the error using the validation. That's going to give me one round of the k-fold. Because I'm doing 5-fold, this is going to go through 5 times. It's going to give me 5 different validation errors, and then we're going to take the average at the end. So I'll run it again here, and you can see that the cross-validation error for degree 8 was 19, roughly 19.2. So definitely much higher than what I saw in my one case here, where I happen to probably have an unusual validation set. And it's also much closer to the actual test. Again, we're not usually using our test data set, right? But I did it once at the end of our last lesson. And so 20.8 is pretty close, right, to what we see here with this 19.2. So this is much more reasonable and giving us a better ballpark of the type of error we'd expect from our test set. Okay, so I already picked a model of degree 8 when I did this. So I want to repeat this process now. Let's do it for a model of degree 2, model of degree 3, model of degree 4, right? Let's do all those same degrees and get our cross-validation error and see which one is lowest. So this next part of the code is just going to generalize what I did above, but allow us to change the degree of the polynomial. And again, it's using functions out of the scope of this class, but just so you know that's what's happening underneath the hood, I'm just going to be able to increase degrees and then calculate my cross-validation. So that's what I'm calling here. I am calling this function, train with cross-validation, for different order degrees, and I'm going to do it for 5 folds. So I'm letting my folds just be 5 here. The degree, I'm going to start at 0 and go up to degree 10. So I'll actually have 11 different models I'll be playing around with here. And for each of those 11 models, I'm going to be calculating the mean squared error for 5 folds. And then I will average the mean squared error over those 5 folds and come up with an average mean squared error for each of those 11 models. So that's what you see here. What's getting spit out is degree 0 model, my average mean squared error, degree 1, my average, degree 2. And you can see that technically the lowest one happens with degree 5. So I'm happy to stop there. But if you're noticing, it's actually not even that much better than what happened with degree 2 or 3. So these would also be reasonable stops, at least based on just your mean squared error. It would be great at this point to use other metrics like your residuals and or adjusted R-squared to decide, okay, where exactly would you stop? For our purposes, I'm just going to stop at the 5th order, and then we'll actually calculate the actual test error. So I'm assuming the test error is going to be pretty close to 18.3. It's probably going to be a little bit more. But I'm also going to point out that look at how these numbers are bigger than what we saw up above when we were doing this for our specific validation set, which is letting you know that our validation set was probably an outlier. It wasn't that representative of what's really going to happen in the test set. So putting all of our eggs in this basket is probably not as useful. And that's the beauty of k-fold cross-validation. It really helps us try to see if we had maybe an outlier for our validation split. So scrolling back down, let's calculate. So at this point, I'm going to use the 5th degree polynomial as our model. And once I've done that, so I'm going to drop the 6th, the 7th, and the 8th order here. And I'm going to fit my model using all of the available data I have, not the test, but the mini train and the validation, right? Because I've finished using the validation to help me pick my model. And now that I have the model, I'm ready to get its best fit parameters using all the information available. So once I do that, I'll have my final model, and then I can use my test data set once to get my final result. And here, there we go. So my test mean squared error is just slightly bigger than my cross-validation error. It's right around 20. And again, this may or may not be a reasonable stopping point for us. depending on what our goals are with this model. And also I'll point out that this is not in units miles per gallon. This is in units miles per gallon squared. So it may be useful to convert these to root mean squared error before deciding, like, is this low enough? Now, I'll point out all we did here was work with one of our available parameters. And so in the next part of this code, I'm actually going to have us add in more parameters. And the code behind it, I don't want you to get too bogged down. I want you to think conceptually of what this is representing. The code behind it, I'm using a lot of that sklearn pipelines just to make it faster. But what I want you to realize is happening underneath the hood is now where I'm going to take into account, okay, like cylinders and weight and acceleration, all these other features that I hadn't incorporated before. So I'm going to just scroll past. You can just run these cells. You're welcome. Well, these ones right here are just redoing my test train split. But you're welcome to learn more about the pipeline codes I have. But I'm going to scroll to the pictures because that's really what I want you to understand. So I'm going to create 5 or 6 different versions of this model using pipelines. The first version of the model is just going to have, here, I'm calling it here, you'll see, it's right here. It's going to have horsepower and horsepower squared, right? So that's basically what we did above, but this is now all in this new code. And then I'm going to add up to the 5th degree. So it's basically exactly what I did above, but I'm just writing it like this and I'm saving it in this dictionary. Okay. So why is this important? Well, now let's try adding it. Let's take this horsepower plus horsepower to the 5th and start adding in more features. Let's try to add in cylinders and displacement. So that's what this code is doing here. Okay. And now at the end, I'm saving it to this. And right now, I'm just going to output our training error. Okay. In a minute, we will calculate the cross-validation error for all of these as well. But let's just keep track and see if our training error is getting better. And I have converted it to RMSE in this code just so we have it back in the units of miles per gallon. All right, so I did cylinders and I did displacement. Now I'm going to point something out. This gives me RMSE of 4.26. Up above, I had 4.25. So it's slightly increasing, okay? Not enough for me to think, oh, throw those away. But maybe I want to do something a little bit different with them. And from knowledge of cars, displacement per cylinder may be useful. And so that's actually what I'm going to plug in. Okay, so again, this is part of the feature engineering part where you're just playing around with adding new features and seeing what they do to the model. So here now is that new model that has horsepower up to the 5th. It has cylinders, displacement, and displacement per cylinder. And I definitely decreased my training error here. Okay, so I'm going to now do more features. So you can see all these versions of the model I'm playing with. I'm now going to think of adding in weight and acceleration. And when I do that, there's weight, there's acceleration, I get a new version, and I'm also getting my training error to decrease. Okay. But now I'd like to stop and say, okay, great, but what's really happening with my cross-validation error? And so that's what we're going to look at here. This code is doing the same thing that we were looking at above. It's just applying it to the form that I have here, and mainly it's going to put it in a way where we can visualize. So all of these pieces here are to get us to this beautiful visualization. Here are my 6 models I've created so far. And again, I'm representing what's in them with this little notation down below. Okay, so I'm doing something you should never try at home, which is I'm plotting the test RMSE. I'm plotting it in light blue to reiterate the fact that we shouldn't be actually looking at it, right? So I made it kind of invisible-ish, but this is just for demonstration purposes. So you can see how it compares to training and cross-validation. In each of these cases, my training is decreasing, which we'd expect, and my cross-validation is higher than my training in each of these cases, which is also, expected, right? Usually it is higher. What's interesting is my test is slightly lower than my cross-validation, but it's pretty close to my training in these two. Again, there's no way I would know that in the real world. So I like to use cross-validation as the best proxy I can for my actual test error. But so far, all of this looks good in the sense that I'm adding more features and I'm not overfitting. My cross-validation is not popping up to be much higher than my training. So this says to me, keep going. Like, you can keep adding parameters. Let's see if you can get your root mean squared error even lower. How low can you go? So now I'm going to add model year. Now I basically have all of the features that we have available in the data set. And when I add that one, I really improve both my cross-validation RMSE and my training RMSE. So this is, again, great. Like, if this were part of my process, I'm on the right track. So then I can say, well, let me keep going. And the one piece of data I have not used yet, let me scroll back up so you can see all the data here. Okay, so I haven't used name. I also haven't used origin. That's okay, but let's say I just jump to and I say, oh, I want to use name. So out of the scope of this class, we have not covered how to transform data like this into a form we can add to the model. It's basically an extension of one-hot encoding where you do it with text, okay? And so that whole process is out of the scope. I have included a little hint or a little information about it at the end of this notebook just so you can see. But I am just going to pop the code in. So the process that we're going to use to basically encode our text information is called bag of words. And it's built into sklearn through this count vectorizer function. Again, all of this out of the scope. I'm using this as a demonstration to help you see when you might start to overfit. Okay, so for the purposes of this, you don't need to know how to do bag of words, just know it is available. And so I've added that now as my model, or the name. That's what I'm calling N for the name. And see, now look what happens. So that's the data here. And so it looks from the training perspective like, whoa, we're doing amazing. But then the cross-validation has huge red flags, right? Because all of a sudden it's much bigger than your test than your training, excuse me. And it went up, right, from my last model. So that right there is your red flag that you're overfitting at this point. So if these were the only models I had to choose from, then at this point I could say, all right, well, let's choose this one, which has my lowest cross-validation error. And it also has my lowest test error, which again, I wouldn't know without looking underneath the hood. But if you go to do that, we go finalize the model and we say, okay, that's the one we're going to pick. We fit it to all of the data we have available, and then we, at the end, use the test once, and then I could see, oh, I did great. I got it pretty low. Again, I should look at residuals. I can also look at multiple R squared. So this is not the only metric, but for the purposes of understanding how to use cross-validation to determine when you're overfitting, that's what I really wanted you to see from this visual. Now, what is the limitation of this? You may be noticing what one of these limitations is. So one of them is it's very dependent on the order in which I'm adding, or very dependent on like which combination of parameters I want to include. So you notice I just did it additively, but I could have looked at all possible combinations. Like, what if I do horsepower and leave out cylinders? Or what if I do displacement and leave out weight? I didn't look at all possible combinations of this because it's very computationally intensive to do this, especially if you're using k-fold cross-validation. The other thing is it's going to require your complexity to vary discretely, and there's not necessarily a natural way to order your models. So rather than just adding one feature at a time, what we're going to look at in our next video is how we can fit a large model. We can include all the possible features, but apply constraints on the sides of the coefficients. And this is the notion behind regularization. So this is another way we can come across or choose our best model without having to do it so manually. So we'll go to that, we'll look at that in the next video, but before we do, I just want to recap some of the findings from this notebook, and I'm also going to give you a couple practice questions from the slides. So to summarize, we've looked at how we can use cross-validation to help us check and make sure we're not overfitting. And so when selecting between models, we choose the one with our best cross-validation score. We looked at two techniques for how to compute that. The first was the simple holdout method, using our training set to fit parameters and a validation set to calculate our validation error. This is also called simple cross-validation. And then we looked at k-fold cross-validation today, which will help us account for any type of abnormalities that might be in our validation set. Let's actually practice conceptually what's happening underneath the hood of the k-fold cross-validation calculation that we were doing in the code. So in this case, we were using cross-validation to help us tune or find our best degree polynomial. The second case, we were using cross-validation to help us tune or find our best combination of features for our model. For each of those models, we were running cross-validation and then computing the cross-validation error and taking the average across all of our folds. So if I tell you that we're performing a 4-fold cross-validation on 4 different hyperparameters, and again, and the hyperparameters we used in this class or in this example were just powers of the polynomial, but we're going to see in the next lesson how it can be some other types of values that's going to show up when we do regularization. So for now, these are analogous to just having 4 different versions of your model, right? And then here's your 4 folds. So based on this, which model, which lambda, should we select? Take a minute, put it on pause, and see what you can do. Okay, so what I want to think is for a fixed model, let's look at a fixed model, for example, here. I want to see what was the average, because inside here are each of my mean squared errors. So what was my average mean squared error? That's your cross-validation error right there. And so for my second model, it's this one. For my third model, it's this. So I want to pick the model that has the lowest average cross-validation error, which is going to be lambda being 0.2. The other thing I'm going to point out in this process is that there's 16 mean squared errors that get calculated in this process, right? Because I have 4 different models and I'm doing 4 folds. Which leads me to the next question. Suppose I wanted to select our best polynomial degree out of 5 possible options, so 5 possible models. How many times will we compute the mean squared error during 4-fold cross-validation? Okay, so for each of our 5 possible options, I'm calculating the mean squared error 4 times. So altogether, I'm going to have 20 mean squared error calculations that happen. I will be averaging, right, for each model, average the 4 that come from the folds. So at the end of the day, I will end up with 5 averaged cross-validation scores, and that's what I will use to select the best model. But underneath the hood, underneath all of that, there's actually 20 mean squared errors that went into this process. So one thing I'm going to point out is this can easily become very computationally expensive. Suppose, again, this was me just adding some features and making up some features that we could use to predict miles per gallon. And if I wanted to decide which of these 9 features to include, well, really there's 2 to the 9th different models, right? If this is me just having you visualize, right? Do we include horsepower? Do we include displacement, right? Do we include each of these things? The problem with this is the runtime is exponential in the number of parameters. And so this can become computationally infeasible very quickly to do k-fold cross-validation through all possible combinations. And that's where the method of our next video called regularization can come to our rescue.